Hi, welcome to the last talk of the day. I hope you got enough sleep last night. This is about implementing the Scala 213 collections. My name is Stefan Zeiger. I'm a member of the Scala team at Lightband. And we just released Scala 213 yesterday. The major feature is the redesigned collection library. The main goal was to make it easier for users with better discoverability, better error messages, so no more use cases in the Scala docs, no more can build from leaking out in error messages when things go wrong. But it's also easier for collection implementers because it's more regular. But there's still plenty of necessary complexity, so I'm going to show you how to implement different collections. Before we get to the actual collections, though, I'd like to start with a type called IterableOnce, which is not quite a collection, but it can be consumed by many collection methods. IterableOnce basically means it has an iterator method, so that's similar to iterable in Java, except that in Scala with IterableOnce we also allow types that only allow a single traversal. Most importantly, iterators. So iterator extends IterableOnce, and its iterator method just returns itself. And this is a lightweight interface that doesn't have any of the additional methods that you would previously find on types like traversable ones, so it can be implemented easily by non-collection types. In particular, we now have option implementing IterableOnce. This was not true previously. So let's see what you have to do to implement IterableOnce yourself. So this is the simplest thing you can do. You just extend IterableOnce, in this case of int, and you define an iterator method. That's all you need to do. There are two more things you might want to add though. One is override known size, if you do know the size, because it can be used to optimize certain collection operations. If you look at the bottom, there's this example where I'm creating an array buffer and then adding an instance of an IterableOnce. For 3 elements, it doesn't really make a difference, but if you have a lot of data in there, the array buffer may have to regrow several times in order to fit all the data. But if you override known size, then it will pre-allocate that correct size. The second thing you may want to implement or override is the stepper. Stepper is a type that was previously part of the Scala Java 8 compat library and is now in the standard library. So a stepper is basically like Java's splitterator. It allows both parallel consuming of iterator-like things, and it also allows primitive specialization for int, long, and double. So, and here we do this just by delegating to data.stepper, which gets a stepper from an array. If you look at an actual usage, this is something we can do with a stepper. So first we get the stepper by calling .stepper, and this is actually of type int stepper. It's not just a stepper of int. This explains why we need this strange functional dependency here with the stepper shape. So stepper shape computes the correct stepper type for whatever element type we have. That's because we need to support Java's primitive specialization. So now we have an int stepper, and if we call Java iterator, it will give us a primitive iterator of int. And then when you call next, this is actually a primitive int method, which doesn't involve any boxing or unboxing. You could use the same code at the call side without overriding the stepper method, but the default stepper implementation just goes through iterator. So that means it will box primitives and it will not support parallel processing. Okay, let's move on to the real collections though. We'll start with something like this. We're going to implement a sequence of elements with arbitrary types. It's supposed to be immutable and have array-like performance characteristics. So it's basically immutable.ArraySeek, which exists in the standard library. We won't do the real thing, which has 450 lines of code, so it might get a bit bad to read at the back of the room if I put it on a slide. But the size is mainly because it supports all the manually specialized versions for primitive types. We can do a simple version which just keeps its data always boxed in an array of any. So we have our class mySeek, which extends some type and contains the data. So let's see which type we should actually extend here. We have a few different abstract collection types to choose from. At the top level, there is collection iterable. That's the basic type of a collection. And it is extended by immutable iterable and mutable iterable. In general, you do not want to extend a type like collection iterable. Always pick the immutable or mutable version depending on which you implement. At the level below, we have types like seek. And again, there are three versions of seek. There is a collection seek, there is an immutable seek, and there's a mutable seek. And it works the same way for all of these types. The immutable and mutable versions always extend both their immutable or mutable parent type and their generic version in the collection package. So to keep this diagram a bit simpler, we are going to collapse them like this. And now we can take a look at the full hierarchy. We start with iterable, and we have seek below it on the left, and it is further divided into linear seek and indexed seek. A linear seek is one that supports an efficient tail operation, and an indexed seek supports efficient apply and length operations. So depending on how you want to consume them, you may want a linear seek or indexed seek, and of course, depending on what you have in your implementation, you usually want to extend one of the two, but it's perfectly fine to extend the generic seek too. Purely in the mutable universe, we also have mutable buffer, which is a seek that allows growing and shrinking. Then next to seek, we have both set and map. They are based on the standard equals and hashcode contract, and they are extended by sorted set and sorted map. These take an additional ordering constraint, and they keep their keys or elements in case of a set in this ordering. Map is further extended by seek map, which is a map that has a seek-like ordering for its keys, so they are by insertion order. And finally, we have the views. There's a view type extended by seek view and map view, but you don't generally extend them if you want to implement collections. If anything, you may use them in your implementations. Seek view and map view just add some specific operations for views that come from seeks or maps. You may be wondering, why are they not actually seeks or maps? Well, that's because of equality. Equality is defined at this level. So every seek can only be equal to another seek, never to a set, map, or view, even if they contain the same elements. And since equality has to be transitive, you cannot implement more than one of these top-level types and still get equality correct. Okay, so the one that we want is the red one here. That's immutable index seek. So let's do that. So we add extends index seek of A. And there are two methods we have to implement. They are length and apply. The implementations are pretty straightforward. Again, we just forward to the array methods because we want to do the simplest possible thing here. I added one other feature, which is to override class name, just so we get the nice output here in the console. This was done with some reflection hack by default in previous versions, but we removed that because it just leads to confusion. And now with this in place, you can create a new mySeek, and you can call for each or index where or any number of other collection operations. And this already works quite well. But it's a bit ugly to create it by calling the constructor and passing this internal data structure that you're not supposed to see. So the next thing I'd like to do is to add a factory implementation. Every collection usually has a factory in its companion object. So we have object mySeek, and we extend seek factory of mySeek. There is no specific index seek factory, so we take the next best thing by going up in the hierarchy, and that's seek factory. And a factory has to implement three methods. They are empty, new builder, and from. You will see the same pattern in many different instances further on. Empty just returns an empty instance, and because we have an immutable collection, it makes sense to always return the same one. So we have a cached instance that we return. Then there's new builder that may be familiar to you from the Scala 212 collections, where you always created a builder in order to build a collection. But that is strict building only. It doesn't support lazy collections like stream or the new lazy list. That's why we have two versions now. The basic one is from, which also allows lazy building. Imagine passing an iterator to from. It takes an iterable once, so you can pass any iterator, and then just returning some wrapper which never consumes the iterator. So this is a lazy collection. This is the way you build it. And you can then later consume the iterator one by one as needed. So array already has a from method, so we can reuse it and we just wrap it in a MySeek. And we're done. New builder works the same way. We have to return a builder. The reason why we have new builder in addition to from is because for strict collections, it's usually more efficient to use a builder. So you always have both. You could implement one in terms of the other as a default, but I looked through the collection implementations actually, and there is not a single case that I saw where we use this default. We always override them separately for performance reasons. So that's what we're doing here too. Array has a new builder method, so we reuse it, and again, we map the result in a new seek. So let's use the factory. We have the usual factory methods available out of the box. Just by implementing these methods, we can call things like tabulate, or we can use it here when converting an existing collection to a MySeek. So this works. But not everything works. We still have these two cases to deal with. So one is an example of one case, and the other one is a bit different. We'll see the difference on the next slide. We're calling filter and map here, and the values you get in the result are correct. That's exactly what you expect, but the types are wrong. So both return an index seek, but not a MySeek. That's what we want. And the index seek is implemented by a vector. That's because vector is the default implementation of the immutable index seek. So why is this? Well, we extended index seek of A. And this in turn extends a trait called index seek ops. And index seek ops has these type parameters. They are called A, C, C, and C. C is the collection constructor, C is the collection type. In our case, the collection constructor is index seek, and map returns an index seek of B. And the collection type is C, which is index seek of A, so filter returns an index seek of A. We always use this C type when we don't change the element type. So that means when we reuse elements from the current collection to build a new collection, as in filter. If we have to change the element type and build some instance of the collection with new elements, we use the CC type here. So what can we do to improve that? Well, as you can see here, both are covariant. It's plus CC and plus C, so we can override them and specify subtypes. So that's exactly what we do. We extend not just index seek of A, but also index seek of ops of A, MySeek of A. So we're overriding the inherited versions. And the compiler would complain at this point because the types no longer match, so we have to implement an iterable factory, which is just the factory that we previously implemented. And this gives us a MySeek constructor, basically. That's the way to build a MySeek instance. So this corresponds to the CC type. And in order to also get the C type right, we extend iterable factory defaults. We will later see how to do this manually. You have to implement a few more methods for this, but often the pattern is that C is just CC of A, and in this case we can use a defaults version. And now we have a fully functional collection implementation. Everything that you want to do with an index seek works with this thing. There's just a few more optimizations you may want to make. First, everything we extended so far are traits. And if you extend a lot of traits, you generate a lot of bytecode due to the way the encoding works. So we have a few abstract classes that you can reuse to reduce the bytecode size. There is no abstract index seek, but there is an abstract seek. So what we can do is to extend abstract seek with index seek. And then, as I mentioned, the default of building collections is lazy, which is not always the fastest for strict collections. Since we're building a strict collection, we have a special strict optimized trait that we can use instead. So there is, again, no strict optimized index seek ops. So instead, we extend index seek ops with strict optimized seek ops. We just use the best available one, which contains the optimizations for our type. And finally, it would be nice to make it serializable, and we have a default serializable trait that works for any standard collection kind, so you get the same serialization that most of the standard library collections use. There's nothing else you have to do about it, because it just uses your factory and the iterator to perform the serialization. And the only thing left to do now is to optimize based on the actual collection implementation. So usually you want to override some methods to make them more efficient for the data structure you implement. So, for example, map. Previously in 2.12 there would have been some can't build from shenanigans, and you need to get a builder and have some special cases in there. That's all gone. So the map method that you override looks exactly as you would naively write it. And the implementation is totally straightforward. Yeah. This is just a simple example where we use the array to our advantage, and we return a mySeek in the end. There's nothing special about this. Okay, let's take a quick detour at this point and talk about collection kinds. So we'll first start with kinds from type theory. So in type theory, kinds are used to classify types, like types classify values. So basically a kind is the type of a type. So we have the standard, or in the standard type theory we have proper types, which are of kind type, just written as a star. And that is the kind of type that a proper value has. Every value in your program has a type of kind type. And examples are string, int, but also list of int. A value can have a type list of int. Next, we have unary type constructors of kind type to type. These use some Haskell-like notation. There's nothing specific for Scala. I didn't want to invent it here. These would be, for example, list or set, or mySeek that we just implemented. That's a unary type constructor. It takes a single type argument. And then we have things like binary type constructors of type to type to type. They are written in a curried version because, again, it comes from Haskell. Like a map, it takes two type parameters and produces a proper type in the end. That's not quite enough for Scala, though. We'd have to extend it to support upper and lower bounds and variants. That's something Adrian did in this paper I'm linking here. So basically, we have to add an upper and a lower bound to every proper type. Like this. And we have to add a kind annotation to the arrow. This is really not important for what we're trying to do. I'm just giving you some background here. So the kind of the immutable map would have this plus arrow here because there's a plus on this type parameter. And for any ref map which has a constraint that the key type must extend any ref, we would see the same thing here in the kind. But even these Scala extended kinds are not enough for the collection kinds that we want. So what we need to do mostly is track context bounds. A context bound is similar to a type bound, but not quite. The main difference where we deviate from the type theory definition of a kind is that a type with a missing context bound implicit cannot be instantiated, but it is still a valid type. Basically, when you have a violation of a subtype bound on a kind, the type itself is invalid, but we care not only about valid types, but also about being able to instantiate these types and their values. So that's why we use this extended, not quite correct definition of kinds. We have a few different standard kinds that we support in the standard library out of the box with different abstractions. We've already seen iterable in our MySeek implementation. That's just type to type. And there's both an abstract collection type for this, and there is a factory type that you can use for this kind. Then we have map, which is a binary type constructor. Let's skip the scary one for now. Let's look at sorted iterable. That is really just an iterable with an additional ordering constraint on the element type. So that's a context bound on the element type. And now if we look again at the scary one, at the evidence iterable, this is really a sorted iterable where we abstract over the ordering. So it's not only ordering, we first have to get this type in, which is also of kind type to type, and then we can use it as a context bound. So it's a further generalization of ordering related iterables, of sorted iterables. But we do not have an abstract type for that, because what does it mean if a collection takes some arbitrary context bound for its element type? It doesn't have any meaning, so there cannot be an abstract collection type. But we do have a factory because we know how to construct these by giving it this context bound. And then next to sorted iterable, we have sorted map, which is the same for map types with an ordering constraint. And we have specific iterables. For example, bitset. These are already proper types, and they also are supported directly with a factory type. So if we go back to our type hierarchy, let's look at where these collection kinds show up. We see them here. But there's an inheritance hierarchy here. So what does that mean? Well, it means that every map is not just of kind map, it is also of kind iterable because it extends iterable. And every sorted map is not just of kind sorted map, it is of kind sorted map, it is of kind map, and it is of kind iterable. We have to implement all the different kinds for these collection types. So how would we do this? Well, it goes back to the CC types, to the collection constructors that we use, because these are different for the different kinds. And the way we do this is by having separate ones for each kind. So if you look at the definition of map ops here, slightly simplified, it takes a CC type parameter, which has two type parameters itself. It's a binary type constructor here. That's our map CC. But the CC it passes on to iterable ops is not this CC. That's just iterable. So these are separate CC types for each kind. The same for sorted map ops. It takes a CC, but the one it passes on to map ops is just map. Generally, you don't care about these inherited ones. You only ever want to refine the most concrete one, but you could refine all of them if that's what you need in your collection. So maybe it becomes clearer if we look at an actual implementation. So the simplest one we can do here is a map. Let's start with a factory this time. There's a special map factory type, and the implementation looks very much the same as the other factory that we've implemented. There's really only one difference here. The three methods we have to implement, empty, from, and new builder, now take two type parameters. That's the only difference. What they do is exactly the same, and we implement them in the same way, basically. There's also a custom builder implementation that I wrote here just because there wasn't anything really fast enough in the standard library to reuse. So these are all also pretty simple to write in a few lines of code. But the main takeaway here is that these factories all look the same except for the parameters. If we were to implement a sorted map factory, it would again be the same, just with an ordering constraint on all these K types. So if we look at the actual collection class, myMap, what I'm doing here is wrapping a mutable Java hash map in an immutable Scala collection. It's not something you want to do in practice usually for performance reasons, but it's easy to implement. So we extend some abstract map type. We mix in strict optimized map ops, which has key and value type parameters. It has a CC type, the one for map, and it has a C type, my map of the key and value type. The same basically as MySeek, just with the two type parameters instead of one. We also extend Map Factory defaults because, again, we have this relationship. We have my map of k, comma v for my map and k and v. So all we have to do is override a Map Factory method. You'll notice that this is now a Map Factory. It's not Iterable Factory. This was a bit tricky in the old collections because they didn't have any factory abstractions in this way for collections that are not of iterable kind. Now we have them. So we do not override iterable factory. In fact, we inherit this one. The one I commented out is the one we inherit. Iterable factory is just immutable iterable because we do not change the iterable CC type here. We only change the map CC type, so we override map factory. For the actual implementation, there are 4 methods we need for the map. We need to get an iterator, then there's a get method which returns a value. There's a remove method that creates a new map implementation without that value, and an updated method that creates a new map with a new binding. The implementation here is fairly straightforward and uninteresting. Instead, let's look at how you would override methods for performance. So I showed you earlier that we overrode the map method in MySeek with a custom implementation. So we can do the same for my map, except there are now 2 map methods, and that's because we implement 2 different collection kinds. So we have 2 map methods. The first one is the one from MapOps. It takes both a key and a value type parameter, and it applies whenever your mapping returns another key value pair, because then you want to get another map back, in this case a my map. The second one applies when you return something else that is not a key value pair, and then you just build the iterable. That's the map method we inherit from IterableOnce. If you override one, you generally should override the others and just call super. That's because of the way implicit overload resolution works. So the compiler might otherwise get confused which one you want to call when they come from different points in the hierarchy. So it's always best to override all of them, and only in one of these you would put your actual implementation. And this applies generally to all the methods that return a CC. Because we have different CC types at the different levels, any method that returns a CC will be overloaded at that level. The most important ones that you see in the standard collection ops traits are map, flat map, collect, and concat. So these are the ones you usually want to override in this way. So what about non-standard collection kinds? I've shown you a few of the standard ones, but maybe you want something completely different. And you wouldn't be the first one to want that, because we even have them in the standard library. They're just not worth adding any abstractions for them. But these are just individual implementations of collections that support even other kinds. The first one is any ref map, which is a map whose key type must be a subtype of any ref. So if you recall the slide about the extended Scala types, we have to take this supertype and subtype constraints into account, so it's a different kind. So we need something more specific than just map for it. There's also int map and long map, which are maps that have int or long respectively as their key types, and you can only parameterize the values. Then we have bit set, which is always a set of int. It sounds simple enough as an implementation, but we'll get back to that in a minute. And finally, there's collision-proof hash map. That's a new map implementation in Scala 2.13, which uses an ordering to to combat excessively bad performance in case of hash collision attacks. That's something that can happen in the 212 map implementations. If someone produces deliberate hash collisions, you get bad performance in a hash map. So this can be used as an attack vector. The Java hash map has a clever hack for that. It checks if the type implements comparable, and then further checks with some reflection magic if it's comparable to itself, and then it performs this optimization, just hoping for the best, basically. But in Scala, we have ordering as a type class, and generally you don't implement comparable, so this wouldn't work for your custom type. So instead, what we do is you get a map that has an ordering context bound for the key type, but it is not a sorted map. That's the main takeaway here. It needs the ordering constraint, but it's not a sorted map, so it cannot use the standard abstractions for sorted maps. I don't want to show you any full implementations for these types. We're just going to look at individual features. They are mostly the same problems you will encounter in all of these, but it's easier to see in some than in others. Let's start with immutable bit set. So you can see we extend strict optimized sorted set ops, and the CC type is sorted set, and the C type is bit set. It is not sorted set of int, because if you map from a bit set and return int values, it would be nice to produce another bit set as the result. That's what all this can build from magic did in 212. So that means there is no factory defaults trait. The factory defaults traits are only available if you have this correspondence that C equals CC of A. So what we do instead is to implement a way to produce a bit set, the C type, directly. Again, there are three methods, and they should be rather familiar to you. They are empty, from specific, and use specific builder. It's basically a factory for the C type that we have to implement. And we're doing this similarly to the other collections by having a bit set factory, but that's not an override, and we're not implementing anything. That's just a convenient way of writing it, and then we're delegating to this factory. But if you forget about those or what the exact signatures are, the compiler will tell you. We were previously in a state in like 212 milestone 4 or 5 where we had some abstractions where you could actually forget this, and due to some unsoundness in the compiler, it wouldn't tell you that you forgot to implement them. So we changed that. There's a bit more boilerplate now, but it is safe. The compiler will tell you when you forget this, just like it will tell you when you forget to override the factory. So let's move on to the collision-proof hash map. As I mentioned, it requires an ordering for the key type, but it is not a sorted map. But we still add a sorted map factory here, and that's perfectly fine. We only extend map ops with map, so there's no sorted map ops to be seen anywhere, but we can use the factory because the factory just cares about how to build this. And in order to build this, you need to give it an ordering for the key type, the same as for a sorted map. There's nothing really sorting specific in the factory type, so we reuse it. Here in Inmap, we can see it extends strict optimized map ops of int, t, map, int map of t. So of course we have the same problem again with the default trait. We have to implement our 3 factory methods. I'm not showing them here. Instead, what I want to show you is yet another map method. Because if you call map on an int map and you return a pair whose first element is another int, so this thing here, it would be nice to return another int map and not just a map. So again, we overload it here. That's another overloading of the map method. We already inherit the other 2 ones from map and iterable, and we can overload it again. This is something you would have avoided in earlier Scala versions, mainly because type inference just didn't work for these overloaded methods. You would have to annotate every call side with the precise type, so you never did this kind of code, but we greatly improved overload resolution in Scala 2.13, so you can easily do things like that and have the compiler figure out all the types. And the implementation is something you will commonly see if you write these abstractions. This is basically the baseline implementation of most methods in the library, at least the ones that are not specific to strict collections. You create a view for the operation, which works because we already have this operation. We already have map implementation, so there's a map view for that. So we just wrap this in a view, let the view figure out how to do the map, and then use this int map from method that we provide here to build our int map from the view. Of course, you can optimize it further, but this is a reasonable default just to get the basic signature in there and to make it work. And here's the Inmap Factory. The most interesting part about it so far is actually that it's not really interesting. It doesn't extend anything. It's just a simple object. There is no abstraction for building an int map. The type theoretic kind of it is the same as for iterable, but of course building it works differently. You need pairs of int and that other type to build an int map. And we don't have a factory type for that, so you can just implement whatever you want. You build your own factory here. We have the usual methods to make it look like the other factory. So that's what you generally do, but you're free to do whatever you want. There's one piece that's missing, though, because, well, if you went to the keynote yesterday, Martin told you there is no more can build from in Scala 2.13. He is technically correct. There are actually two of them now. And they are called build from and factory. But having two sounds worse, but it's actually better because you have one axis here, you have one axis here for these two. And can build from previously gave you all this area in between, and all that has gone away, all the complexity in there. Now we only have factory to enable building driven by a static type, and build from for collection building driven by a dynamic type, when you already have an instance of that collection and you want something of the same dynamic type. For a concrete collection implementation, so not for defining new abstractions, this doesn't really make a difference, because if you have a concrete collection type, then static and dynamic type are the same. So it's just the same boilerplate you have to write twice for both of them. And not having can build from is also correct in the sense that all of the methods we've seen so far have not used can build from. You will only find one or two methods maybe in the whole collections library that use these types. They are very rare and only used in corner cases. Both of them have two different ways of using them. One is by an implicit conversion of the companion object, which sounds strange at first, but it's quite natural and you've already seen it used. So the typical one for factory is this. You have an existing collection and you call the to method on it, and you just pass some other companion object. And this works for an int map, even though int map doesn't extend any of the standard collection factory types. And it works because int map provides an implicit conversion to factory from this object. And the other way of using it is with an implicit instance for the type. I've written implicitly here just to show you how it works. So we're conjuring up a factory from int to list of int. I'm writing implicitly because there is not a single abstraction in the standard library that actually uses this. But you can use it in your own code if you want to. This can be useful for stuff like type-driven serialization or deserialization. That's the use cases we had in mind. And then future build from is actually used typically in this way. The main use case is for future.sequence. So we have an iterable of future of int. And this iterable could be anything. It could be a vector or list maybe. And if you call future.sequence, you will get a future of iterable of int. It just swaps the two type constructors. And it would be nice to have the actual implementation of those iterables be the same as the one you put in, even though statically you only know that it's an iterable. And that's what build from does. So if you put in a list of future of int, you will get out a future of list of int, not statically, but at runtime. What you can also do is rely on the implicit conversion of the companion object and just append this. So this is usually the implicit parameter here, and instead we're passing a list. So that means build a list. That's the replacement for collection.breakout that you may have used in 2.12. But it only works in these very specific cases like future.sequence where it is actually used. So here's our Inmap Factory. This looks like a lot of code, and it is, but it's boilerplate, so there is not much to it. What we have is a factory. We can just use a singleton object here that we cast to whatever type we need. And again, it has the same methods that we've already seen. There's a from specific, and there's a new builder method that we implement, and both are straightforward. And then we have an iterable factory method that returns an implicit factory for whatever type. And we have a toFactory method that takes as a dummy parameter this object itself and converts it to that type. So this wires up factory. And then we have exactly the same thing again for build from. The only difference here is really that these methods additionally take a from parameter, but we don't use it anywhere because we don't care about the object, because the static and dynamic type are always the same. So the implementations are the same as they are for factory. Okay, we're getting to the end. So let's sum up what we hopefully learned, or what I tried to show you at least. The first thing is that the integration of non-collection types can be done via IterableOnce. IterableOnce connects the sequential collections from the standard library and the parallel collections, and also Java 8 streams for both sequential and parallel iteration. And it also supports unboxed iteration of collections. Then we used collection factories, and we saw that there is no special treatment of iterable kinded collections anymore. All the different kinds are on equal footing, and they're all supported. And you can add your own abstractions, just with a bit of boilerplate for build from and factory. And these last two types replace can build from in a simpler and more directed way. If you'd like to know more about the architecture of the 213 collections, there is an overview document called The Architecture of Scala 213's Collections, which was rewritten for Scala 213 specifically. It's on docs.scalalang.org. And the main collection documentation on that website has also been updated for 213. So if you go there, you'll find two different versions for 2.12 and earlier, and for 2.13 now. And you can find the demo project with these types whose implementations I showed you, and some sample code to run them on my GitHub together with these slides. And if you want, you can follow me on Twitter. Thank you. I think we're out of time. Is that right?
If people have questions or you have time.
There's a question.
Yes. Is there any movement for collections that are kind of exceeding the size of the int as indexing, so that you have like lists that are indexed by long instead of int?
I remember seeing a ticket about that, but we didn't do any work in this area. Oh, that's right. Accumulators, they support this. That's another type for integrating with parallel collections and Java 8 streams.
Yeah. Thanks for the talk. Are we expecting the same architecture for Dotty, or is it going to change again?
I expect some minor changes in 2.14, but that's basically it, because 2.14 is a compiler-focused release, not a library-focused one. So it will just be standard maintenance, and then Dotty or Scala 3.0 will use the 2.14 collections verbatim, because it uses the exact same standard library.
Thanks for your talk. You talked a bit about collection breakout in the case of the future, but how is it going to work if I want to map a collection to a different one without having the overhead of double conversion?
You use an iterator generally. Call iterator, and then almost all of the collection methods are also on iterator. In some cases, like for map methods that may not be on iterator, they're probably available on view, so you can call .view instead of .iterator. And in the end, you just call to and build whatever you want from it. There's another one up.
Hi. I just want to know if we can use non-standard implementation to have type proof in pattern matching, like receive in IK.
Sorry, I didn't understand the question.
Can you use some kind of new features to be type proof with pattern matching if I match a case list of ints and list of string, it won't work. It's both lists.
Yes, that's right. You'd have to get a class tag somewhere for the element type from your context. So that's just due to erasure. So there's really not much we can do as a default in a standard library. There is class tag, and that's what you need to use. So you have to wire it up yourself, basically.
Thank you.
So there's a Scala fix rule to migrate to 213 collections.
Yes, in the Scala collections compat repository, there's a set of rules to perform the migration.
So one of my coworkers, Shane Delmore, told me to ask you. He tried it, and the code broke because there's like a mismatch between immutable and mutable collections.
Yeah, that's right. I already replied to him on Gitter about this.
Okay. What was so he wanted me to say basically you should be more opinionated, but I have no idea what's happening. So,
well, we are
people
opinionated. That's why this rule doesn't exist. So the thing here is you can get some breakages because seek in 213 is now immutable seek by default. The same goes for indexed seek. So the easy thing to do would be to provide a rule that changes every existing seek and index seek to be of the generic collection dot whatever kind. But that would not be idiomatic 213 code, because in most cases you really want an immutable seek or an immutable index seek, and it was only not immutable by default, just accidentally in 212. And it's good if you go through your code and update those to be really immutable and only use the generic ones where you need to. But it would make sense to have it as an optional rule, just to do the easy thing.
so does your rule take the generic one and then convert it into an immutable one?
As far as I know, there is no rule at the moment to do any of that. But it would be a nice addition to have one that just annotates the types, basically. So when you just use scala.seek, it would change it into scala.collection.seek, so you get the same thing.
Okay, cool. And how would that be added to Scala collections compat?
Open a pull request.
Cool.
I have never actually implemented a rule myself, so you'll have to ask Julien or someone else who actually worked on these. I only know that they exist.
One last question.
So there is a trait for strict optimized operations, but does this mean that the collection who implement this trait has all the operations implemented as a strict, so optimized to be strict, or we have still variability depending on the method call?
So whether a collection is strict or lazy, first of all, depends on how you build it. If your from method builds it in a strict way by consuming the iterable once that it gets, then your collection is fully strict, because building it always consumes the source. So this is just a performance optimization. We overrode the methods where it makes sense to override them to get better performance.
But at that point, all the operations are overridden to be more optimized to be strict. Or
The ones where we
still
saw an
have
improvement
some
or where it made sense, or possibly not all of them because we just didn't manage to benchmark every single operations. But the critical ones where we noticed it's better to implement them in a strict way, or they were previously implemented in a strict way, those are overridden.
There is a documentation about what is implemented and overridden?
There is no documentation. You'll have to look at the source and see what it actually overrides.
Thank you.
But again, it's just a performance optimization. It's not about strict versus lazy. Everything is strict if you're building the collection in a strict way.
Thank you very much.